Okay, hello everybody, welcome to my video on virtual work. So what we're going to be doing in this video is kind of give a really quick introduction to virtual work. It's not going to go into too much detail, but we'll basically motivate with a simple example and then see how we can solve for deflection for trusses. So this will basically lead on to the next video where we'll talk about how we can use the method of virtual work to solve for truss deflections. So before we actually go into virtual work, let's recall what we mean by work. So work is not in like the normal work in terms of you working towards getting a good grade in the exam. When we talk about work, at least in engineering and physics, what we actually mean is mechanical work. So we say work is done when the point of application of the force moves in the direction of force. So we more formally work is actually the dot product. Basically this is the symbol for the dot product over here. So what happens is work is the dot product of the vector force and the vector which is the displacement of the point. So when we have a dot product, it basically becomes FD cos theta. So if we have a point like so, and then I apply a force and then it moves to somewhere over here, we are basically measuring this distance here. If the point moves from here to here, we basically, since the distance along the force is the same, we are actually doing the same amount of work. So in case we have basically apply a force like this, and the point moves from here to here, right? The point basically moves in the opposite direction. Your work basically is negative. So that's where the cos theta comes in. So if basically the f and the d vector are an opposite in sign, basically f and d both are vectors, then the work is negative. So work is actually a form of energy. So if f and d are in the same direction, work is positive, and you're kind of adding energy into the system. If f and d are in opposite directions, you're basically removing energy from the system. So generally this makes more sense if you have kind of potential energy that kind of gets gained. So basically if you have a mass like this and the object basically moves up because you apply some force here, the potential energy of the system actually increases, and then you can think that this work is actually doing, or rather this force is actually doing some work against gravity. So a simple example to illustrate basically what happens when you have a force and then it moving against gravity, or how the work is done. So imagine you have an object like this. So it has some mass m, and then you have the gravity acting down like this, right? So now I'm going to apply a force F on this object, and basically my aim is to keep it in equilibrium, and then potentially my F is basically moving this object from this location to some other location like so. So this is going to be H. So now if we can think about the work done by this force, so that's going to be this. So the work done in moving this mass because of this force is going to be the force times the distance over here. We can do the same thing. We can think of gravity also being a force, which is basically the weight of the object, in which case the force is basically going to be the mass times the acceleration due to gravity. So it's going to be m times g. So the work that's going to be done basically moving this mass up by this direction h is going to be mg times minus h. So what is the total work done? So it's going to be the total work done is going to be the work done by this force, and added to it is going to be the work done by the weight. So it basically gives us F, this is just the normal multiplication, so F times H minus mgh. So at this point, we can basically think of it in two ways. So on one hand, if we are already great in physics, and then we basically know for equilibrium, F needs to be equal to mg, then we can infer from this equation that if you substitute F equal to mg, that this term basically becomes 0. Right? This is fairly straightforward. The alternate way of doing it is you can basically say that the total work that's done is going to be 0 because the system is in equilibrium. You basically say if the system is equilibrium, no force actually does any additional work. So then what we can do is we can say, okay, I don't know these two are actually equal. What I'm going to do is basically equate this to 0. So that's the second thing we do. So we basically say F times h minus mgh equal to 0. And then I'm going to cancel this h term over here. And then I can conclude basically that F is mg. This is basically the same concept. So you don't actually get an additional equation, just that if you don't know one of these parameters, for instance, if you assume you don't know F, you can basically use the method of virtual work to, or rather method, like we haven't come to virtual work yet, but we can basically use this method to calculate the force value. So the concept of virtual work is similar to the actual work itself. The only difference is that either the force or the displacement that we use is kind of imaginary. So because it's imaginary, we can basically come up with any rules that would basically benefit us. So what we say is we will assume that the virtual force, if you're using the virtual force in our calculation, we'll assume that it doesn't do any additional deflection, or it doesn't produce any additional deflection. If we basically assume a virtual deflection, we'll assume that it doesn't produce any additional force. The rest of the physics we assume are still maintained, so we can't come up, if you make up everything, then it wouldn't really help you and it wouldn't help you solve any of the problems. So what we do is we assume rest of the equations are valid. So if the system is equilibrium, forces need to balance. If the system is connected, if you're doing a virtual displacement, all the displacements or the distances it moves needs to match up properly. So basically, if we apply a virtual force, it's going to be useful for determining an actual displacement. If we apply, a virtual displacement, it's useful to calculate the unknown force. So previously we did kind of a calculation to do the like we activate an actual force of a 1 Newton force, but it's not needed. What we can do is we can basically make it into a virtual force and then make our life a little bit easier. Okay, so now what we're going to do is basically use the method of virtual work to calculate this force tension, or the tension in this rope of the pulley over here. So this is basically the weight. We're kind of like it's acting down here, and then we need to determine how much this tension is, and then we'll use the method of virtual work. So we already know from statics that this value needs to be W over 2, but nonetheless humor me and then let's see if we can solve this using method of virtual work. So for that, what we need to do is first examine what happens when we try to move either the weight or the tip of the pulley by a particular distance. So notice that the rope actually travels twice the distance. So if the weight needs to move down by 1 unit, the tip or the location of this force moves down by 2 units. So if we compare, what happens if we basically just draw the diagram, assuming this distance from this point to this point is d. So what will need to happen is that the rope needs to, because the center point itself moves down, this point will move by a distance d here, and the rope needs to expand on this side by d as well. So there is going to be 1d here and then 1d here. So the total distance this force moves, so t moves by 2 times d. Right? So now if you assume this is going down by distance d, So we can think about the work done by W. So I'm going to unfortunately use the same thing. So it's going to be W sub W is going to be this little w times d. The W sub t is going to be t, and here is where you need to be careful. So when this moves down, the tip also moves down. So basically we are moving in the same direction, so this becomes t times 2d, the same like the displacement of this point and the tension on the same side. So next what we do is basically equate these two, and then we notice that the d would be common. So basically this d would basically cancel out. That leaves us that t would be equal to w over 2. This is something we kind of knew all along, but it's another way of actually getting this on top of the equilibrium equation. So now we're going to examine what happens when we make things slightly interesting. So we're going to assume here that we already know that the force in the spring is going to be F would be W over 2. Now what we previously did was we applied a virtual displacement. Now we're going to do is basically apply a virtual force. So basically I'm going to pull, in addition to the original 1 Newton force, I'm going to assume that I'm applying a virtual 1 Newton force which doesn't make any additional deflection on my object. So if I think about what will happen, so if I have the spring over here, what basically happens is when I apply one additional like this weight, this basically is going to expand. So we are interested in finding out how far this point would have deflected because of this force, or rather because of the weight, and then we having that spring over here. So in order to do that, what we do is we basically apply this 1 Newton virtual force. Now we basically have two things that are happening. Let me write this again. So I'm going to use the blue here to denote the real forces. So let's do real. And then this is going to be the virtual. Okay. So maybe I should have written this in red. So I'll just underline this in red, and then this is going to be in blue. So what will happen is in the spring, the real force is going to be W over 2. The virtual force, I can apply any value here, but because I have chose to apply 1 Newton, the virtual force is going to be 1 over 2, kind of with the same argument here. So basically this 1 Newton virtual force will also distribute on the two sides, and then we get half. Now what is going to happen is we're going to have a real deflection. We'll call that D. The deflection due to the virtual force from our assumption is going to be 0. So this is the thing you need to keep in mind. Now what we basically do is, it's kind of like a tricky assumption. We assume that this 1 Newton virtual force had always existed, and then whatever extra displacement happens is also doing work against this virtual force. So when we do that, basically this point here moves down by a particular distance, and then the spring here is also going to expand by a particular distance, right? So how much does this, so if the spring constant is k, the distance, so basically the spring, this is the distance of the tip here, so this is for the P. So let's see, d sub P would be our displacement of the spring, or d sub S. So because of this W over 2, what basically happens is that the spring would have deformed by W over 2 divided by K. We basically assume that the spring doesn't deform because of the virtual force. There is no additional deformation because of the virtual force. So what we actually do is we multiply this value over here which is the virtual force inside the spring, and then we multiply it by the real deflection. So this would basically give us the internal virtual work. So we'll basically say Wi for internal is going to basically be my virtual force. It's going to be half in red because it's a virtual force, and then times this real displacement. So basically W over 2, and then that divided by K. Sorry, this should be divided over here, and that divided by K. Right? So the virtual, basically the external work done, which is basically going to be here, is going to be, let's call this WE. So here, the virtual force here is going to be 1 Newton. So this basically becomes 1. And then times, so we're interested in finding out how far this point moves. So if this is basically D, that's basically what we written here. We're going to multiply by D over here, excuse me. Right? What we basically do is basically equate this guy to this guy, and then we can basically solve for our deflection. So I'm going to clear the screen and then show you how this looks. So we're basically going to equate these two. So what we did was we're going to equate, let me still maintain the same color. So we basically had W by 2K. This is basically the real thing. So multiply this by half. And we're going to basically equate this to the actual force, like basically the external value. So the external displacement, which is going to be the actual displacement, is going to be D, and then times 1, which is the virtual force, virtual displacement. So this basically gives us D would be equal to W by 4, W by 4K. So keep in mind that instead of this 1 Newton, if I basically used P Newtons here, this basically becomes P, this becomes P, and then I'll basically cancel out these two P's, and then I'll still get the same result. So that's the reason, to make life easier, we kind of started with a 1 Newton force. So this kind of summarizes how we can potentially use the method of virtual work to calculate the displacement. Now I'm just going to motivate you to discuss about why we would use method of virtual work rather than actually try to solve for the deflection of the truss. So imagine you have this truss like so. Basically you have a 100 Newton that's being applied here. So we know that we already know the internal forces, right? If this is 100, this is going to be compression of 100. This is going to be in tension 141.4. And then this is also going to be in compression 100. So if you're not sure about this, kind of revisit the discussion on method of sections and method of joints, and then you can solve for these particular values. So now if we separate these out, kind of put them apart, so I'm kind of hidden the nodes. So let's see what is going to happen here. So basically, because of the compression, this link gets longer. So this gets longer. These two get shorter because they're in compression, right? So you're basically squishing them, so they become shorter. So now if we try to assemble them, so I'm going to put the node here, kind of I bring this guy here, bring the other one here, and then try to see what happens. So now there is basically a gap. I mean, obviously I've exaggerated the distances. Basically there's a gap here, and then we're going to have to rotate these objects like so to actually basically assemble this together. So notice that it's not very easy to calculate the deflection. What is typically done in finite element calculation is basically you kind of assign displacements to the joints, and then you use that kind of create a matrix and then try to solve for the actual displacement in both directions. What we'll do in the other video is basically use the method of virtual work to solve for this reflection and then use the same thing to solve for redundant trusses. Thank you.